Okay, good evening, everybody. I'm Mark Schellhammer in the faculty of the School of Medicine at Johns Hopkins. Let me get a little bit of logistics out of the way first. There will be a question and answer session at the end of this talk. Hopefully, I will time it appropriately so that we can have an active Q&A session. You can submit your questions by putting them into the chat box. The chat box, by the way, is only available for people with an actual personal computer. It does not work on mobile devices or tablet computers. But if you enter your question in the chat box, it will be relayed to me. If it's a question that's relevant to an immediate clarification of something that I may have screwed up, then that will be sent to me immediately. Otherwise, the questions will be deferred to the end and we can address them later. So I'm a faculty member at the School of Medicine. I've been here since I started as a postdoctoral researcher back in 1990. Before that, I was in graduate school and supported some experiments on the space shuttle using a module called the Space Lab module that ran in the back of the space shuttle during the 1980s that studied space motion sickness in astronauts. So it is very much the case that vomiting astronauts put me through graduate school. And so for that, I am grateful for them. I came to Johns Hopkins, again, 30 years ago, did a lot of work in more fundamental neurobiology, got back into the spaceflight business, and have been doing that very actively for about the last 15 or 20 years. For 3 years, I took a leave of absence from my academic position, and I was the chief scientist at the NASA Human Research Program from 2013 to 2016. So relocated to Houston for that period of time. So if you go outside after this talk and want to complain about the Baltimore weather, let me assure you that in Houston, this is what we call a nice day in the summertime. I'm going to talk to you about the biomedical challenges and issues of sending people to Mars. And when I talk about biomedical issues, I'm talking about biomedical in the broader sense of not just physiology and medicine, the things that we think of as biomedical, but also much more broadly, some of the psychological issues, cognitive issues, the way that you design missions to optimize health and performance and minimize the biomedical challenges. So we're going to cover a lot of material and obviously not all of it in detail. I will also say that along the way, I'll be talking about the way that NASA approaches this problem and the way NASA approached these issues when I was spending time there. But I do not, even though I'm wearing the t-shirt, I do not speak for NASA. I'm speaking in my own capability as an academic researcher. So why are we talking about Mars and the biomedical challenges of sending people to Mars? Well, what you're looking at now is a slide that depicts NASA's current plans for human spaceflight. And this calls for a return to the moon with humans by 2024. That's in 4 years. I don't think we're going to actually accomplish this in 4 years. Nevertheless, there's a lot of effort going into it, and it's a great driver for the program because lots of fascinating problems in terms of engineering, in terms of human capabilities in sending people back to the moon to stay for weeks or possibly months at a time. But you can see that even in this lunar plan, up in the upper right-hand corner of this figure is a picture of Mars. And this indicates that NASA thinks very much of flights to the moon as partly a way station on the way to Mars, a place where people can go and refine their techniques, address the issues of living off of Earth, and be ready to go to Mars in maybe 20 years or 25 years. So this slide is a little bit older, but it indicates in the kind of the bigger picture the context of where Mars is. So over on the left-hand side, right now we use the International Space Station. I'm going to talk about that a lot. It's in low Earth orbit, about 250 miles up. The next set of plans, phase 1 on this chart, called for going to the moon, maybe orbiting the moon. Now we're talking about landing on the moon. Again, using that as a way station, proving ground for then going on out to Mars. And here's what we're up against when we start talking about going to Mars. So first of all, The top slide there, the top picture is the space station. When people are on the space station, and at any given time, there's usually 6 people on the space station, a mix of Americans, Russians, and various other nationalities. For the last 20 years, almost 20 years exactly, there have always been people on the space station. So if you are less than 20 years old, there has never been a time in your life when people have not been in space. And when I was 20 years old, that would have seemed like science fiction to me. But that's the reality of where we are now. And right now, they are in low Earth orbit. There's real-time communication with the ground, mission control in Houston and in Russia. There's one in Russia as well for the Russian segment of the space station, are in constant communication with the crew on the space station, whether that crew likes it or not. And sometimes they don't like it because it can be burdensome, addressing questions from mission control and knowing that they're being watched all the time. Nevertheless, when there's an anomaly, when there's a problem, it's real helpful to have real-time communication, immediate communication. That communication, by the way, also includes communication for medical issues, communication as a countermeasure for some of the psychological concerns of being in a small space for a long period of time with a small number of people. So astronauts can essentially make a phone call to family, friends, physicians, psychologists, pretty much anytime they want to. And that's huge. That is very beneficial to their psychological well-being and their medical well-being, obviously. There's good evacuation capability. If there's an emergency, including a medical emergency, a crew can get back from the International Space Station to Earth on a matter of hours, days at the most. And there's constant resupply of consumables, a variety of different spacecraft, some commercial. Regularly send supplies up to the space station. Fresh food, for example. They never have to go very long without fresh food. When you get to flights at the moon, whether they're in lunar orbit or actually landing on the moon, there's still near real-time communication. Communication delay on a matter of a couple of seconds, round trip. There's still evacuation capability in an emergency, but now we're talking about days, at least 3 days just to get back from the moon, and that's after getting off the surface. And there's limited resupply of consumables. It takes a long time and it's really hard energetically to get things out to the moon. So you start to see some of the issues that you're going to have to address when you get to Mars, when you're at the moon. Now, Mars is the thing that really gets your attention in terms of the logistical difficulties. No real-time communication. Best case, in the vicinity of Mars, you're talking about a one-way communication delay with Earth due to the finite speed of light, electromagnetic radiation, on the order of about 20 minutes. So if there's a medical emergency and you call back home for help, you can expect to get that answer in maybe 40 minutes. That's if the Earth and Mars are not on opposite sides of the sun at the time, in which case there's no communication at all. So the crew will be largely autonomous on their own. Essentially no evacuation capability just because of orbital mechanics and energetic considerations. When a crew gets a certain way on a mission to Mars, and a mission to Mars would probably be about 3 years, about 6 to 9 months on the way out, similar on the way back, and staying there for about a year to a year and a half, waiting for the planets to align appropriately so that you can come back with the least energy expenditure. But once you get to a certain point on a Mars mission, maybe a month in, maybe a few weeks in, you are going to Mars. The crew could get a debilitating disease. Somebody on the crew could die. The rest of the crew is going to go to Mars and complete their 3-year mission. So this focuses your thinking in a whole new way. There is no evacuation capability. And certainly when you're at Mars, there's no way to get back earlier than intended. And no consumables resupply. So when you're at Mars, you're going to be depending on the things that you took with you or the things that you pre-positioned. And that will include things like food, some medications. Those turn out to be issues because of shelf life. Now, another way to think about this problem is, you'll see that the background of my slides is a view of Mars. That is the Martian surface there at the bottom, from one of the Mars rovers that NASA has there. And this actually has a view of Earth up in the sky. If you look at the letter C in the word consumables, on the third line down, that little tiny white dot inside the letter C is what Earth looks like from Mars. So the idea of being able to look up out of your spacecraft or the surface of Mars and look at the Earth and draw some consolation from the fact that you will be returning to Earth at some point, that consolation is going to be hard to come by. You are really on your own. Okay, so I'm going to build up to what that means in some more detail as we go through the talk. But in the meantime, let me tell you about what's going on right now on the space station to address many of the issues that will be problematic for a Mars mission. So this is the space station, pretty big, about 100 meters across. Like I said, has a crew of 6 at any given time until there's a crew swap. A swap means 3 people go up and 3 people come down. So there could be at any given time 6 people or 3 people or 9 people if there's an overlap in crews, but the majority of the time 6 people up there. And it is a busy place. Lots of stuff going on there. So here's an example of an astronaut on a bicycle, a cycle ergometer. You can see his feet are on pedals and all wired up. I see EKG electrodes. Clearly they're looking at gas exchange, carbon dioxide and oxygen during exercise. So this probably is an experiment that's being conducted by the Human Research Program to look at exercise capabilities, among other things in space. Exercise, extremely important for reasons that I will get to in detail a little bit later. But on the space station, crews, at least on the American side, exercise for about 2 hours a day, 6 days a week. That's what it takes to maintain physiological capability. A couple of other things going on. A few years ago, astronaut Scott Kelly has a twin, Mark Kelly, who was part of the so-called Twins project, but Scott Kelly was in space for, they called it the 1-year mission, 340 days. Here he is in the big picture to the right, injecting himself with a flu vaccine. This was an experiment meant to, in a calibrated way, challenge his immune system to see if it has changed in space. Immune system function is in fact changed in space, which in ways which we don't completely understand. Over in the upper left, you see, again, Scott Kelly with his 1-year partner, Mikhail Kornienko, cosmonaut from Russia, conducting ultrasound examination of the eye. That's why he's holding that transducer up to his eye. I'll talk about why you might want to do that in space in a few minutes. So let's talk about astronauts versus the rest of us, versus mere mortals, and the challenges that they face and how we have to put into context who these people are. It is, astronauts are, at least in terms of medical issues, relatively homogeneous. They're all in great shape. They exercise, they eat well, they're motivated, they're well characterized, they're heavily measured, their health status is monitored constantly. Compliance for things like exercise and diet is rarely an issue. In those ways, it is not really analogous to many terrestrial populations. So in some ways, doing research on astronauts is actually a good thing because they're compliant. They're in a well-controlled environment. We measure a lot of things, but it is a small population. There is no way in which you can consider human spaceflight research to be a what's called a big N problem or a big data problem. It is quite the opposite. In the NIH parlance, it would be something like almost an orphan disease. Small numbers of people, in this case, elite numbers of people, questionable how much their health and medical status is generalizable to the population on Earth. Nevertheless, they present very interesting challenges. And here are some of those challenges. This is a list from Space Shuttle, Russian Space Station Mir, and Space Station up to 2006 of the problems, the medical problems that have been most prevalent in NASA astronauts in space. And some of these are not surprising. This, by the way, is not a secret. This information, you can't figure out who got, which particular astronaut got which particular problem, but the fact that these things occur in space is not a secret. This information is available in public NASA documents. So you can see, as I said, many of these things are not unusual for highly motivated, driven people in a demanding, challenging environment. They hurt themselves, they get lacerations, a number of things happen. But there are some things that are a little bit unusual. Insomnia, problems with sleeping, partly because of the schedule and altered day-night cycles, light-dark cycles. Space motion sickness due to what's called space adaptation syndrome. People still suffer from that. Headache due to elevated CO2. So there are many things on here that are unique or almost unique to the spaceflight environment, but few of them will be jeopardizing a mission, a spaceflight mission. They are problematic, and many of them are things that you need to address, but not too many of these things are going to be huge insurmountable problems, especially if you know about them and train the crew properly. So here's another way to look at some of these issues. This is something NASA calls the Exploration Medical Conditions List, the MCL. This is the list of 100 medical conditions that NASA has extracted from things like the list that I just showed you, and just basic considerations of things that would happen to small groups of people in a demanding environment for a long period of time. And again, you can see that many of these things are common, not unexpected, pretty much well controlled. There's one intriguing one there, which I have circled, something that NASA calls somewhat euphemistically behavioral emergency. Behavioral emergency is a psychological episode, an issue, a panic attack, probably not going to get something like that, but severe depression, mood changes, interpersonal relationships. Hard to get hard data on this, but some of these things have occurred in space. We know about some of them, especially in the Soviet program before the Russians started working closely with us. Those are very intriguing, and we will come back to those. Okay. So I'm going to leave you with a number of take-home messages over the course of the talk. Take-home message number one has regards medical issues before we get to the research end of things. Space is a nasty environment for humans. There's relatively high radiation compared to being on the surface of the Earth. It's a weightless or zero-G environment, which has many advantages, but also many disadvantages, which I will get into. Some of the disadvantages are related to the fact that things don't fall to the ground, to the floor. And so astronauts have a tendency to get things in their eyes, to sometimes breathe in things, dust, dirt, that would otherwise fall out of the way. It's a small, isolated, confined environment, a small number of people. If there's a toxic problem with something toxic within the environment, that's a huge problem because you can't just open the window and air out the cabin. Many things can go wrong. You saw a list of many of the medical conditions. Obviously, there are other things. It's an operational environment. It's inherently dangerous going into space. Things can go bad in a hurry. There have been fires on space stations, on a Russian space station Mir. There have been decompression events in addition to the medical events. And yet we expect a lot from astronauts. We put them up there at great expense, and they have been trained for many years, also at great expense. And we put them in a very challenging environment and expect them to be at their peak, to perform almost flawlessly in a very demanding environment. And to a great extent, they do. Astronauts are very impressive people, and they rise to the occasion. But as missions get longer and more demanding, especially when you're talking about something like a Mars mission, 3 years, it's unrealistic to think that people can be at their best and maintain peak performance over that entire time. That's the reality of the situation. We have to address that. And what makes that especially intriguing, as I said a number of times, the crew will be largely on its own. Autonomy and independence from mission control, including medical personnel on mission control, will be a requirement. No way around it. And that applies especially in emergency and off-nominal conditions. So let me make this a little bit more acute. Here's part of the problem for Mars. This is not Mars, obviously. These are pictures of the crew when they come back from 6 months on the International Space Station and land in Kazakhstan. And assuming that they come down where they plan on coming down, which is usually the case, there is immediately a crew of people, a large crew of people that go out in helicopters to help the crew, help the astronaut crew and cosmonauts literally get out of the spacecraft. In some cases, they have to be carried out, lifted out, literally. And they are immediately put in chairs, like you see on the right view there, because some of them will have problems walking, not because of strength issues, but because of coordination issues, because their brains, their neurovestibular systems have to now accommodate for the fact that they're having to take into account gravity for the first time in 6 months. And this turns out to be an issue if, for example, there were an emergency on landing and the crew had to make an emergency evacuation from their spacecraft. The fact that they really cannot walk or run in any meaningful sense immediately after landing is a huge problem. And as far as we know, when we send the crews to Mars, there will not be a huge number of people there to help them get out of their spacecraft and walk. So this is one of the challenges that drives NASA's research program. So I'm going to start to talk about the problems, the medical and biomedical problems from the research end. But there's a lot of them, and it's helpful to figure out a taxonomy, to put this in a context for categorizing these things. So NASA looks at these things in terms of the hazards, the physical hazards that impact human risks, the biomedical risks. And you can see them outlined here: altered gravity, physiological changes that come from them, distance from Earth, crew autonomy, and other things, a hostile enclosed environment, small space with a small number of people. That's also isolation and confinement. And space radiation. I'm not going to talk too much about space radiation today. That's a whole topic on its own. NASA is currently revising dramatically their views of the space radiation problem. Depending on who you talk to, space radiation is either going to kill you outright before you return from Mars or not have much of an impact at all. It almost certainly will increase an astronaut's likelihood of getting cancer over the course of a lifetime, but that's a problem for after the mission, not during the mission. Okay, and under each of these, you can see that there's a number of more directly biomedical issues. So I'm not going to go through those here. You'll see these coming up in some of these slides. I'm actually going to skip that one. Let's go to this one. This is a chart that pretty much directs what the Human Research Program does. So this is something called the Human Research Integrated Path to Risk Reduction, the PRR, as NASA likes to use its acronyms. And this is a timeline. So it goes out from, this is a few years old, so this starts at 2017, but it goes out to about 2030, which is how long NASA thinks they can keep the International Space Station going, which is required to do a lot of this research. And NASA categorizes the biomedical issues in terms of red, yellow, and green. Red means it's likely to be a problem. There's something that's likely to happen in this area, and it's likely to have some bad consequences, like maybe killing somebody or debilitating them or giving them some lifetime medical deficits. And you can see that there are a number of things that are red. And the job of the Human Research Program is to sponsor the research that takes these red things and turns them green. In the meantime, in the course of doing that, sometimes you have to turn them yellow first, which means that you've come up with an intervention or a countermeasure that you think will work, but it has to be validated and verified in a certain number of people. That's very problematic because, again, spaceflight is not a large N problem. So if this were an NIH type of study, you would do perhaps clinical trials in which you would run hundreds or thousands of people to validate and verify an intervention or a countermeasure. For NASA, we'll be lucky if you can do 10 or 20 people. And that's huge. That's hugely problematic also because of human variability. and you're putting people in a challenging environment that has not yet been completely characterized, especially when you're talking about a Mars mission. So lots of unknowns here, but nevertheless, you mitigate the problems that you know that you have, which are listed here along the left-hand side. You can see that the first three issues there are radiation related. As I said, NASA's evaluating now its radiation stance in terms of research. But the next one, cognitive or behavioral conditions, what NASA calls BMed, behavioral medicine. Those again are the psychological issues. And then it goes from there, and you can see the range of problems. There's about 25 or 30 of them that NASA considers important enough and has yet unsolved to perform and sponsor research for. So I'm going to talk about a few of them. I'm going to pick 2 or 3 of them on subsequent slides and talk about them in a little bit more detail. But here are the ones that I'm only going to gloss over to give you an idea of the range of problems. Food and nutrition. So as I said, a lot of the supplies, food, medicine, is going to have to be pre-positioned at Mars because you can't afford to take it with you because of mass and volume constraints on the spacecraft. So they will be pre-positioned on Mars years ahead of time. So you need food that is not only nutritious and palatable, but maintains its viability in a slightly enhanced radiation environment and altered atmosphere for a long period of time, several years. So this is not trivial. Now, I don't know about you, but I know we have things in our pantry here at the house that have been there for several years, and I would not be comfortable eating them, especially if I were on Mars. So this turns out to be a real problem. Renal stones. So far, kidney stones have not been a huge problem for people in space, but the bones lose calcium in space because they're not loaded by gravity. I'll talk about that in a minute. And that calcium has to go somewhere. That calcium goes into the bloodstream and then makes its way into the urine, where the urine can be supersaturated with calcium. And since there is not the normal gravitational assist to clearing fluid out of the kidneys, at least that's one of the prevailing ideas, that calcium can aggregate, and form kidney stones. And a kidney stone on Mars would be a real problem. The next thing, something called human system interaction. This is the crew getting along with the systems including the possibility of artificial intelligence for clinical decision support. In other words, assistance with medical interactions. Semi-automated systems on the spacecraft just to help the crew with mundane or dangerous tasks. This is a huge issue. If you've ever had to fight with Microsoft or Apple software to get it to do what you want it to do and what you think is so obvious, that's just a taste of the problem that you would have with an astronaut crew on something much, much more ambitious. You'll need to know that you can trust the automated system, in this case with your life, and that it's going to give you feedback if it doesn't understand something like a human crew member would do. Pharmaceuticals kind of speaks for itself. The same problem with food and nutrition. They might have to be supplied at the moon ahead of time. Immune system function. There are changes in immune system function. We don't completely understand them. One thing that is apparent is there is reactivation of latent viruses, herpes virus, for example, shingles, smallpox, not to the extent that the crew exhibits the disease, but they start shedding the virus. It's reactivated in space. And that might not be a problem on its own, but we don't understand why. What is it about the particular range and confluence of stressors in space that would cause this to happen? And is it the harbinger of something that's worse that could happen on a 3-year Mars mission? Same for alterations in the microbiome, the gut microbiome, which is useful for not only digesting food properly, but also, in some cases, maintaining proper cognitive function. There's a cognitive microbiome connection. Sleep speaks for itself. problems with cardiac arrhythmias. Again, so far, not a huge problem in space. It's one of those things that would probably has a very low incidence because of the severe medical screening for astronauts, but if it does occur, could have very dire consequences. Okay, let's talk about a couple of these things. Bone density. When I talk about the biomedical challenges of being in space, people almost always talk about bone because that's one that they've heard about. When you're in space, there is no constant loading of the bones, the muscles, the cardiovascular system due to being in a gravity field. So just by being in the 1G of Earth, just getting up and walking around is actually a form of exercise. I try to tell my wife that every day when I don't get on the treadmill or go out for a jog. She doesn't buy it. Nevertheless, it is a form of exercise. It helps keep your bones intact. And when you go into space, that does not happen. So astronauts will, if they don't do the proper exercise, lose bone mineral density. You'll essentially lose calcium. And I'm just going to look here at measures from the hip. This is the measurements that are in that green box. And this is just basically a timeline going from measurements that were made early on in the Mir space station, 80s and 90s, up through the International Space Station, which are the red dots, using an early form of resistive exercise, the IRED, going to a more sophisticated form of resistive exercise. This is essentially weightlifting in space, but using bungee cords and other mechanisms to supply the resistance. And those are the triangles, the kind of grayish triangles, and then going up to the turquoise triangles. This is resistive exercise plus bisphosphonates, which is an osteoporosis medication. And you can see that this is kind of a success story. These, especially that black bar that you see on the last set of symbols, the turquoise triangles, is just about at the zero marker, the zero indicator on the axis, on the y-axis, which indicates no change. Now, there is significant variability, which we don't completely understand. So in some ways, we're happy, or NASA is happy, the community is happy with the countermeasure of exercise and possibly bisphosphonates to address bone mineral density. But here's the big secret in this. Bone mineral density is not necessarily the same thing as bone strength. In fact, you can lose density, you can lose calcium from the outer part of the bone, the so-called cortical part of the bone, and from the inner part, the so-called trabecular part of the bone, which is a honeycomb structure that actually gives the bone its strength. And the measurements that led to this chart were total bone mineral density, including both types of bone. So we don't yet have a good way to convert bone mineral density to bone strength, fracture risk, which is the thing that we're really concerned about. And why is that? Well, it's because to the extent that we do know how to relate bone mineral density to bone strength, those measurements and those analyses are done in people on Earth who have problems with bone demineralization. And they tend to be elderly people, and especially people with osteoporosis and people who are not active. And that does not apply to the astronaut corps. So again, this is a problem in which you could look at bone mineral density. Loss of calcium in space has almost an orphan disease. Here, by the way, is what the advanced resistive exercise device looks like, the one that has been so successful. On the left, it's being used in space. On the right, it's being used, tested and demonstrated on Earth. It's good. It's effective. Look at how big it is. We are not going to take this to Mars. We just do not have the capability on a rocket to get this to Mars. So current challenge for NASA is to figure out how to take this thing, which is like almost as big as a car, and make it almost as big as a shoebox. Okay, another problem. This one is very intriguing because it just started to show up maybe 10 years or so ago, after we had been sending people into space for about 50 years. Started to take people by surprise, and this is a real challenge. This is something called SANS, Spaceflight Associated Neuroocular Syndrome. So I'll say that again, Spaceflight Associated Neuroocular Syndrome. The words are kind of vague because they indicate that don't really exactly know what's happening here. We know some of the effects, and we have some theories about why it's happening. And here's the prevailing theory. We've known for a long time that when people go into space, due to the fact that gravity is not pulling fluids down to the lower part of the body as it does on Earth, there is a shift of fluids toward the head. And you can see it here, an astronaut Story Musgrave on the left-hand side on Earth, 1G environment. On the right-hand side in space, you can see how puffy his face is. And astronauts report sinus congestion, number of things like that. You can see it. You can see the puffy face here. Part of that shift in fluids is a shift not only in blood and lymphatic fluids, but also in cerebrospinal fluid, the fluid that surrounds the brain and the spinal cord. And that's what image number 2 there on the right-hand side indicates. The fluid that surrounds the brain increases in space, and the pressure of that fluid on the brain increases, which right there should get your attention, because you wonder if it's going to have a long-term effect on neural function. Is it going to cause damage to parts of the brain? It's a form of mild hydrocephalus, water on the brain. Well, one thing we're pretty sure of is, this is in the bottom part, that this increase in ICP, intracranial pressure, it only has one place to go. It works its way down the sheath of the optic nerve. It works its way down the nerve that goes to the eyeball and pushes on the back of the eye and causes, that's like pushing on a beach ball. It causes the eye to change shape. And that's what you see on those images called globe flattening at the bottom. Those are images, actual MRI images from on Earth, which is the one on the left, and in space, the one on the right. And you can see the flattening there has been enhanced. So what happens when you flatten the eyeball? It changes the optical properties, changes the visual acuity. And this, in fact, is what astronauts reported that drew NASA's attention to this. So that's bad enough when you start to mess up the vision of high-performing individuals in a demanding environment. But again, is this just the canary in the coal mine? Is this an indicator that on a 3-year mission, you might actually see changes in brain function due to some of these same processes? We don't know. All right, I'm going to skip to the last of the detailed issues. That involves behavioral health. So as a sensory motor researcher, a biomedical engineer, this is one of the things that I really didn't think about that much until I got to NASA. The problems of small number of people in a small space for a prolonged period of time. So as if being quarantined in your house with your family during the coronavirus crisis is not challenging enough, imagine doing that for 3 years and there is no way out because there's a vacuum outside. And so some of the problems that can occur from these kinds of situations are listed here. Sleep loss, problems with sleep, circadian desynchrony, workload fatigue, stress, morale, mood changes, cognitive functioning, interpersonal conflicts, challenges with motivation, family separation, personal communication. That's not a problem with the coronavirus, but it certainly would be on spaceflight. So when presented with these things, these are going to be challenges. We know this just from a huge number of other considerations, people wintering over in Antarctica, submarine crews, number of experiments that NASA has performed. But there's often pushback from people saying, well, you know, astronauts are very special people. They are highly motivated and highly trained. They eat stress for breakfast. These kinds of things are not going to stop them from doing their jobs. And that may well be true. On a 3-year Mars mission, it'd still be very challenging. But even if astronauts are able to work through these problems, even if they're able to bite the bullet and get through, we know that these psychological issues have physiological impacts. So down at the bottom, you can see immune changes in immune function, cardiovascular function. We know that those connections exist. So even if they will fight their way through the overt psychological issues and get along with their crewmates for the sake of the issues, sake of the mission, there still could be problems, physiological problems. And I'm going to skip that slide. Let me talk about this one. This is an indication from a few years ago supplied to me by David Dinges, who's at the University of Pennsylvania. He had crew members on the International Space Station for up to 180 days just report very crudely on what's called a visual analog scale. That's a VAS, a stress rating. From 0 to 100, how stressed out do you feel? Whatever you mean by stress at this particular point in the mission, at this particular point in your life. And you can see that this does not augur well for a long-term mission. Now, Dave Dinges, being a good researcher who wanted to point out the potential difficulty of this problem, was nice enough to apply a extrapolation of a cubic polynomial to this stress indicator, which would suggest that by the time you get out to a 360-day, one-year mission, people's heads are going to be exploding in space due to the stress. Now, we don't know if that's the case. They may be finding countermeasures. They may be figuring out ways to mitigate this stress. But nevertheless, we anticipate that this is going to be a problem, and it's one of NASA's biggest concerns right now is the biomedical problem, the behavioral medicine problems, the psychology. So take-home message, there are medical, this is on the right-hand side, there are medical concerns that are an integrated piece of the bigger picture. They can impact the way that the crew carries out the mission. We need to place the medical concerns into the context of the needs of the mission and allow the crew to maintain resilience. I'm talking about medical issues, but also very much psychological, potentially psychological issues. But here is the big picture. Here's what I want to talk about for the next few minutes before we get to the questions. There are shortcomings to this conventional approach. The approach that has been taken so far by NASA, with some exceptions, but it's the approach also taken largely by NIH, largely by Johns Hopkins School of Medicine, by the research community in general, is to look at these problems and address them in a segregated manner by discipline. They look at the cardiovascular problem. They look at the bone problem. They look at the sensory motor problem. They understand that psychological problems may have widespread impacts, but they generally look at interventions for the psychological problems independent from the other things. But there are interactions between all of these systems. They can lead to unexpected effects. And what concerns me about this, it's going to lead to the so-called black swan problem, the thing that you haven't anticipated because it arises from an unanticipated, unexpected interaction of these problems, each one of which you thought you had addressed and mitigated. So this becomes a problem in my thinking of maintaining the resilience of the crew to deal with unexpected problems. So here's a little quote from Ron White in an article from a few years ago. Meeting the health-related challenges of human space exploration requires that one abandon a model of the body that has muscles, bones, and heart and brain acting independently. Body parts do not travel into space. The individual traveler's body must be viewed realistically with all the parts connected and interacting. Easier said than done. This, in fact, is the defining feature of a lot of the research that I've been doing since returning from NASA. Here's just one example. CO2. CO2 level is elevated in a spacecraft. And it's in the space station, it's elevated. It's about 10 to 20 times what it is ambiently here on the surface of Earth, because it's expensive in terms of resources and energy to bring it down from there. And we know that elevated CO2 leads to headache, cognitive slowing, vision changes, lethargy. So this is a well-known problem, but it leads to some other things too. There are changes in cerebral blood flow. One of the ways the body deals with the elevated CO2 and the attendant relative decrease in oxygenation to the blood is by increasing the blood flow to the brain. Well, you've already got a problem with fluid shift to the brain. You've already got too much fluid going to the brain due to fluid shift. The last thing you want to do is have the body increase the blood flow to the brain, and yet that's likely what it does. The other thing, one of the ways the body deals with elevated CO2 and elevated acidity in the blood is by buffering that acidity with calcium. Where does that calcium come from? It comes from the bones. We already have a problem with losing calcium from the bones due to taking away gravity loading. So this is just one relatively simple example of the interactions between these effects. This chart is just meant to show you that there's a potential for a lot of these things. This shows not only the physiological issues like I've just been describing, but some of the psychological issues and the issues of how you design the mission, how you interact with ground control, how you design the spacecraft, and all of these things interact with each other in a network fashion, as indicated here on the lower right-hand corner. And we are just at the very, very beginning stages for starting to look at any of these kinds of things. But like I said, this is the kind of thing that I think is going to drive resilience on spaceflight crews, the ability to provide them with the tools, conceptual and tangible, to be able to deal with these funny interactions, identify when they're happening, and figure out what to do about them. So I will stop on this slide. This recognizes the fact on the left-hand side there, this is not my quote, health is a state of complete physical, mental, and social well-being, and not merely the absence of disease or infirmity. Peak performance and health of astronauts in space is not just a matter of the fact that you've mitigated all of the known problems. It's also the fact that you've provided the crew with the resilience to maintain health and performance in the face of unknown interactions and unknown stressors. And this just delineates this on the right-hand side. There are many interacting parts. There are emergent properties from those parts, and we need to maintain mission and crew resilience in the face of these challenges. So with that, I'll thank you for your attention and take questions. Okay, I see one. Please say a few words about space radiation exposure, potential for high replicating organisms like bacteria developing resistance to normal antibiotic therapy during a Mars mission. Yes, potentially huge problem. We don't know. That's one of those interactions that could spring up and get you. So, I don't have a good answer for this question, so I'm going to elaborate on the question first for a little while. This is one of those things where you could say there's a mutation in an organism that is hiding in the food supply. But, we thought we had solved the food supply problem, and we thought we had solved the radiation problem because we addressed it for humans. And we thought we had solved the immune system problem because we understood what was going on in the immune system and the microbiome problem. But here now is a problem that addresses all of those because an unanticipated mutation due to radiation, 3 years worth potentially of radiation on a Mars mission could alter bacteria that would lead to a problem. And I don't know, I don't have anything really insightful to say about that, except that that's one of the things that the crew has to be ready for. You have to understand if there are antibiotics or other medications on board that could have secondary uses. One of the slides that I sometimes show that I took out of the talk at the last minute is a picture of Kate Rubins, astronaut, certified biochemist, who was on the space station a few years ago, and she was the first person to actually sequence DNA in space. And why would you want to sequence DNA in space? Well, if you have a bacteria that mutates due to radiation, that could be a very helpful thing to do to help you figure out which of the onboard medications or other substances might help you ameliorate that problem. Okay, here's another question. Is SpaceX's timeline for Mars realistic? So, as I sometimes say, Mark Twain or someone said that it's a mistake to get into an argument with somebody who buys ink by the ton or by the gallon, meaning that it's a mistake to get into an argument with somebody who has access to the newspapers in those days. And so the last thing I would want to do is get into an argument with a person who builds its own rockets, especially when it has something to do with space. Nevertheless, no. The answer is no. I do not think his plan, his timeline for getting people to Mars is realistic. But in the meantime, Elon Musk has made it possible for people like me and a lot of my colleagues to talk about sending people to Mars in the immediate future, near-term future, 20 years maybe, without being laughed at. He has made it actually seem feasible because he's accomplished so many other things. So no, look at it this way, sending people on a suborbital space flight, just a little a hop into space, 5 minutes of weightlessness, going from there to orbital space flight, like the International Space Station, I consider that at least an order of magnitude more difficult and challenging and energetic. Going to the moon is at least another order of magnitude. Going to Mars was at least another order of magnitude beyond that. And we have two companies, Virgin Galactic and Blue Origin, who will be sending people on suborbital space flights quite soon, maybe this year, almost certainly next year, but they have been talking about doing this for almost 10 years. And that is a suborbital space flight by commercial companies. Space flight is hard. The energy requirements are very difficult to do safely. Could a series of space stations that allowed for stops along the way help us achieve a trip to Mars? Maybe, but I don't think so, because it would take, if anything, it would have one detrimental effect from my point of view, is that it would prolong the journey. So you would get halfway there or a quarter of the way there and spend additional time in space. Why not just get to Mars? Why not get there where at least you have a gravity field, you have some shielding from radiation due to the fact that you're on a planetary surface. Why not get there as fast as you can? Now, one way in which it might be helpful is if that space station had artificial gravity of such a level that you could start to intervene and mitigate some of the problems that you get from the zero-G environment, which you would probably have on the spacecraft that makes the journey. So my initial answer is no, don't waste your time stopping along the way. But my second, more considered answer is maybe if it has artificial gravity. And artificial gravity, by the way, maybe before somebody asks the question, very compelling for a lot of these problems. If you can avoid the fluid shift and provide loading of the bones, muscles, cardiovascular system, you can address a huge number of the problems. But we have no idea yet how much artificial gravity is enough, what level and what, how much per day, how long a period of time you would need to apply it. Next question, are there any speculations on long-term issues with Mars colonization, generationally genetic issues? Yes. Not yet a lot of thinking on along these lines within NASA, because NASA isn't yet thinking in terms of colonization and settlement. They're still thinking in terms of what they call exploration missions, which is you go there, you spend a certain amount of time, and you come back. And you don't plan on living the rest of your life there. But there are some people, and I've actually co-authored one or two papers with some people who are starting to look at these problems. The problems with genetic changes once you get there, some of which might actually be beneficial. Some of the capacity that we have for surviving in a 1G environment in terms of the strength of the bones, the ability of the heart to fight against a 1G gravity environment, those would not be so necessary if you knew you were going to stay on Mars forever, because the gravity is about 3/8 the level of what it is on Earth. So you could imagine that over the course of time, there may be genetic adaptive changes that work in favor of those colonizers. The problem is they would not be able to come back to Earth. The next issue is, would you want to try to enhance those genetic changes? And these are ethical questions. How many astronauts in the first mission to Mars? Right, how will they be selected? Yes, I'm sorry, I neglected to say that. Current thinking, again, for NASA, is 4 or 6 people. And that depends on a lot of things, including the behavioral issues. You don't want people breaking into cliques. You want to send the fewest people you can in terms of mass, volume, consumables, obviously. Pure engineering requirements call for a smaller number of people. But if somebody gets sick, somebody gets hurt, somebody dies, you need to be able to provide enough capability in the rest of the crew members to carry out very demanding and challenging tasks in a alien environment. You want people to get along with each other, and sometimes that argues for more people. So 4 to 6 people. The selection process, as far as we can tell now, will be largely what it is, because it's been largely successful for NASA astronauts and astronauts from other countries. Highly selective. If anything, it would probably be geared more towards people with a lot of team experience for obvious reasons. You don't need people with a lot of fighter jock experience, you know, the kind of classic astronaut image from the 60s about people who have the right stuff, who are flying spacecraft. That's still important. You want people who are comfortable with machinery on which their lives depend, and people who are very comfortable in emergency situations that can kill you, that could kill them. And that argues for people who have been pilots and things like that. But more and more of their time is going to be spent in long periods of time in a more democratic environment, let's say, in which they have to do scientific explorations and planetary excursions of various kinds. And so that, if anything, the selection process would be geared more toward finding and training people with the skills to get along with others. And they already do that, but it'll have to be enhanced. Is it technically difficult and economically feasible to create artificial gravity to mitigate some of the physiological changes associated with zero gravity? So I addressed that a little bit. Artificial gravity, very attractive, very appealing for several of these problems. It is technically difficult, but if you knew how much artificial gravity you needed, let's say that you know that 0.1 G, 1/10 of a G, for 2 hours a day or 8 hours a day is sufficient to counteract 90% of the physiological problems. Well, then you could have astronauts sleep in beds that rotate and supply sufficient centripetal force to provide that level of artificial gravity, and that's not out of the question. There was, for a time, something called an artificial gravity sleeper at the lab at MIT where I got my doctoral degree. So people have been thinking about that, and that would clearly be a lot cheaper and a lot easier technologically than rotating an entire spacecraft. But until we know the answer, it's hard to make a judgment one way or the other. And the engineers who design the spacecraft and make the hard decisions don't like answers that don't have compelling evidence for them. So part of the answer is, yeah, it would be great to have artificial gravity, but a bigger part of the answer is we don't know. Next question, if you watched it, how accurate was the margin? Thank you. We were talking about this before we started the presentation. How accurate was The Martian with respect to astronaut health, with respect to rationing body recovery to physical injury? Yes, I liked The Martian a lot. Excuse me, a lot. We had something called the Mars Week when I was still at NASA, in which we had the author come out and they had a special viewing of the movie. He gave some talks, including to the research group that I worked with at NASA at the time. I thought The Martian was great, partly because it demonstrated what I was talking about here, resilience on the part of Mark Watney, the astronaut on Mars. He dealt with a string of problems that were largely unanticipated. And the way he dealt with them was largely by applying things that he had on hand in new ways based on a vast storehouse of knowledge that he had. So he was properly trained, and the mission was designed to give him some of the tools, physical tools, conceptual tools, to come up with unanticipated solutions for unanticipated problems. The one thing I thought where it would not, which was not that realistic, and this is going to be my final point, and it takes me back to one of my themes. Near the end of the movie, when they found out that he was alive on Mars and they told his crewmates that he was still alive, but the rest of the crew was nearing Earth and it was time for them to come home after an awful long time in space, the crew voted unanimously to just go back to Mars and pick them up and come back, thereby extending their stay in space by a year and a half, 2 years. And it was done with like no second thoughts, no qualms. Yes, of course, we'll spend an extra couple years in space. I don't think that's realistic because of the behavioral and behavioral and psychological issues that we've been talking about. They may have done it because they're mission oriented, but I don't know if they would have been as glib about it as cavalier as they were in the movie. So something to consider. Those are the issues that are going to be demanding. So if I were to leave you with an issue, resilience. Resilience on the part of the crew, resilience on the part of the way that a mission and spacecraft are designed, because the resilience impacts human health and performance, which in turn impacts the ability to accomplish the mission successfully. So, I'm not that hard to find on the internet and various Johns Hopkins websites. So if anybody has any further questions or wants to engage in discussion, I'm happy to talk about this all day. So with that, I think we have to wrap it up.